Before I introduce the maximum interval of existence, I want to review with you the recent theorem of existence and uniqueness. The results established by that theorem is a local existence of a unique solution. So let's just have a quick review on that theorem. If you think of a theorem, you have to think about the condition. What is assumed in that theorem? With that condition, then we arrived at a conclusion. So here's the assumption by the theorem. So we have an initial value problem. So that is the governing equation, right? That's the initial data. So we are going to abbreviate this initial value problem, as IVP. So that's the problem under consideration. And the theorem assumes the vector field, this vector field, which is a very general case, right? Can be a nonlinear problem, differential equation. Yeah. So this depending on the x. And we assume this vector field is defined on this set. This set, which is a subset of T cross Rn. You see, a subset of R, the real number set, cross Rn, because this is the time variable, right? It's a real number. And the x variable, it is in Rn. So therefore, domain of the vector field is a subset of R cross Rn. And partial derivative of each component of the vector field. So suppose this is the ith component, because if x is a n-dimensional vector valued vector function, and this capital X is also in Rn, because they should match, right? So x, so if we I, that means the ith component. So I is from 1 to all the way to n. So xi means the ith component of the vector field. And each component depending on the x. So we need to do for each component, we do partial derivative with respect to the jth component of this x. So total partial derivative will be n squared, because the range for I is from 1 to n. The range for j is from 1 to n. So total number of the partial derivatives will be n squared. So we just check the partial derivatives. If all of these partial derivatives exist and continuous on B, then we have a nice conclusion, right? With such a nice condition assumed for X, which means if we assume the partial derivatives are existing and continuous, then what's the conclusion? We say we can find an integral curve for the initial value problem. Okay, here's the conclusion. So that is for each initial data, because X, remember our initial condition, X at this time is C, right? Is the C. The C is the, this is the initial data. So that means for the initial data, which is belonging to the set where the vector field is defined on, there exists a solution curve. Remember, this solution curve is a function of t, right? Okay, function of t, so that maps from a time interval to Rn. But t naught has to be a point of this time interval. So there exists such a curve from I to Rn that satisfies the initial value problem. So this is part of the conclusion. That means there exists a solution. The other part of the conclusion is that not only there exists a solution, there exists only one solution. So suppose you think there is another solution, let's call it gamma, which is from a time interval j to Rn with t naught as a point, right, belonging to that interval, because it's from j to Rn. If gamma is another solution defined on from time interval to Rn, then we can show that this solution gamma is identical to alpha, the solution we found already. That means if you think there is another solution, then the gamma has to be the same as alpha over an interval, which is a subset of the intersection. Recall that I is the time interval where alpha is defined on. Gamma is defined on J, right? Gamma is the solution defined on J. So alpha is the solution defined on I. However, I and J, there's a common point because this T naught is in both I and J, right? So that means the intersection is not an empty site. So there must be, okay, this is not empty. And also we can find, suppose another subset Q. So no matter how small it is, there exists such a Q. It is a subset of this over this interval Q. The solution is unique. So this version shows that we actually proved existence and uniqueness over some interval. This interval, no matter how small, that means a local existence. An interval, this Q is near the point, T0. So that is no matter how small this Q is, and we have proved existence and uniqueness of a solution. So once we achieved that local existence and uniqueness, and we can actually show further a stronger result. A stronger result is global uniqueness. The global uniqueness, that is, if you have found a solution, an integral curve alpha, right? This alpha from a time interval, recall that I can put this to remind you that alpha solution from a time interval to Rn. And if you also have found a gamma, another solution over time interval J to Rn, then that means both, since they are both solutions of the initial value problem, they should satisfy the equation, the differential equation, and they also satisfy the initial data. That means alpha at T naught is C. Gamma at T naught is also the given vector C. So if they both satisfy the initial value problem, then we can, with the same assumption, we can show that alpha is identical to gamma. The two solutions should be the same, and they are identical over the intersection, the interval I, intersection of I and J. So compare this global uniqueness. This version is stronger compared to the previous conclusion. So the previous version is that they are identical. There exists a small interval, which is a subset of I intersects with J, right? On this interval Q, and they must be equal. So that's the conclusion we arrived before, which is a local existence and uniqueness. But now if we actually arrive at a different result, this is a global uniqueness. That means we can actually show that over this interval, it doesn't have to be a subset of this interval. Over this interval, for n and t in that interval, alpha and gamma will be always the same. That means unique solution. So this is a global uniqueness of the solution of the initial value problem. And now there's another concept, the maximum interval of existence. Once we have an interval where solution exists, and that interval can be extended until to the largest possible interval where solution still exists. So we can get, in addition to the local version of existence and uniqueness, we can get the largest possible interval over which solution still exists. So here is the same assumption. That is, we just get a stronger result. Yeah. So quick look of the problem is that initial value problem. This is the initial data and vector field defined on the set B, right? B is a subset of R cross Rn, and the partial derivatives of the vector field are all continuous. And with that conclusion, then you see the conclusion, I mean, the assumptions are the same as that local existence and uniqueness. So we now, with the same assumption, we arrive at Okay, so yes, we should go find not only the local existence, then with the same assumption, which is this. And then now we have a maximum interval of existence. So there exists an interval. So this time interval is denoted by I, still the I. Yeah, for the time interval, that this time interval should have this point, because at this initial time, right, t0, we have a data given. So this interval has this t naught. So t naught belongs to this interval. And we want to say for this problem, there is such an interval. Also, always, right, this initial data at t0, the x value is c. So this has to be at this t0 and initial value is c. This has to be in the domain of the vector field. Yeah. Otherwise, the problem is not properly defined. So that is necessary. And the conclusion right now we're getting is there exists a largest possible time interval where solution curve is defined on. And this alpha, it is just a notation to indicate that this is a solution curve as a function of t, but satisfying this initial data. Right? Usually we do not include the parenthesis t, just use the name alpha. Yeah, so this is just a name for the integral curve satisfying this initial data for the problem. And this integral curve is from this time interval to Rn. So that is a time interval, and it is the maximum interval of existence for a solution. That is the alpha defined on this interval. If beta is another solution, also satisfies initial value problem, then this solution, the interval where beta is defined on, has to be a subset of the interval I. So for the initial value problem, so initial data and this interval is the interval, the maximum interval of existence. For any other solutions, that if you think there is another solution defined on a certain interval j, also j has to include the t naught, but that interval is smaller, or it is a subset of the maximum interval of existence. So we just, that means this interval of existence cannot be larger than this one. So that's why it is called maximum interval of existence. Yeah, existence for such a integral curve. So this the interval will have a name, right? We call it maximum interval of existence. And the corresponding integral curve defined on this maximum interval is called maximum integral curve passing through this initial point. Yeah, so this is just a notation for the integral curve that is defined on this maximum interval of existence. So yeah, these two things are related. Let's look at one example. So here is a very simple equation. The simple equation, just one single equation, right? It's not a system of two equations or three. So this is just one single equation, but still it will give you some insight on the concept of maximum interval of existence. So if we solve this equation and we get a general solution, and if we require the solution to satisfy initial condition, and then we can find initial value problem. So it's very easy if we just simply, because dx derivative of x equals x squared, then think you can do the separation of variables, because the dx right over x squared equals dt, and then the x variables and t variables are separated. So just do the integration, then you will have some integration constants. To decide the constant, you have to use the initial data. Then you will find a solution. So this is just something you should know before you take this course. So, and you can find a solution to the initial value problem. After you have found the representation, then let's see what is the maximum interval of existence. And this representation tells us that t should not be 0, otherwise denominator is 0. So the solution is undefined. So t should not be 1. I mean, t should not be 1, otherwise denominator is 0. So if it's not 1, then we exclude 1. So it could be this, right? The t, that means our interval where solution curve is defined. It could be this, or it could be this. Which one of the two intervals? Is it from 1 to infinity, or the other one, from negative infinity to 1? And if you look at the initial data, the 0, which is our t naught in the theorem, the 0 should be part of the interval. So, but 0 is not in this first, so it should be, it's not an option. So 0 is in this interval. Yes, so the other interval. So therefore, the maximum interval of existence is negative infinity to 1. But which notation should we choose? The notation we choose is the I, the interval, corresponding to this initial data, which is 0, 1, right? This I, parenthesis 0, 1, is the notation for the maximum interval of existence. Okay, let's look at another example. Here's another example. Again, we have an initial value problem. So this initial value problem, if you do the separation of variables, you see dx d over dt equals 1 over 2x, and we try to separate x variable from t variable. So we can multiply 2x dx and leave the negative sign here and multiply dt. So that's a separation of the two variables. Afterwards, we do the integral of both sides, right? The left side, you do the integral with respect to x variable. The other side, you do the integral with respect to t variable. So once we have this, then we can find the antiderivative, which is x squared equals negative t plus some arbitrary constant. Let's call it d, the arbitrary integration constant. However, we do have initial data. Let's decide what is the integral curve. After we do integration, then we put, when t is 0, the x should be 1. So the integration constant d has to be what value based on this equation? Clearly, d should be 1, right? So once we know d is 1, then we know the solution. So that is x squared minus t plus 1. So that's our solution. But of course, we should take a square root, right? So x squared is 1 minus t, right? From here, we can get x take a square root of 1 minus t. But now question comes, do we take a plus sign, a positive square root or negative square root? So we have found, okay, we can use either positive or negative, but depending on, if you take a negative, no, you have to take positive because the x value is initially a positive. So that is the hint, right, for us. So x, when initially the data initial value is 1, which is positive. So let's take a positive. Yeah, that's the solution. So we should take a positive square root of 1 minus t. Okay, so we found solution. But for this solution, we have a maximum interval of existence. What is that maximum interval of existence? Let's use that notation. Remember, xi for this initial data, that's the notation for maximum interval of existence. And which interval should we use? Because we cannot, can we use 1? No, because when t is 1, x will be 0. When x is 0, this equation is undefined, right? The right-hand side. So that when t is 1, x is 0, because when t is 1, that should not be part of the time interval. Because in that case, when t is 1, x is 0, then this 1, 0 is not belonging to the domain of the vector field, because that doesn't make the vector field defined. So that's, so let's, for this problem, let's, after we do that, we found a solution, which is x equals square root of 1 minus t. Then we know t cannot be 1. That means the maximum interval for this initial data, maximum interval of existence is either from 1, not including 1, 1 to infinity, or negative infinity to 1. Which side of 1. So we need to think about that. Which side? So here is initial data is given when t is 0, right? So the interval must include the 0. So let's see which side. This one does not include 0. So, but this interval, yes, has that in 0. So 0 has to be in this time interval because initial data is given when t is 0. Yeah, 0 is part of this interval. Then we choose the maximum interval of existence to be the second part. So we erase the previous option, then that's the maximum interval of existence. So we're going to write as up to 1. That's the interval. So yeah, we just learned a concept that is the solution can exist at the largest possible interval, and that interval will be called the maximum interval of existence. So we can extend our the existence and uniqueness, the theorem from turning that result to a stronger result. So to prove actual solution can exist on the maximum interval of existence. Okay, so that is the notation for that interval yeah. So for this specific example, right? So we have notation adopted.